In this segment, we'll look at the Hooke's law graph. Now we'll notice there's some data, some elongation data or displacement data, the force applied in newtons, and we have a graph. This has been labeled as the independent and this as the dependent. So we have the elongation, compression, displacement on the horizontal axis and the force applied on the vertical axis. We'll notice where the 0 is vertically and where the 0 is in terms of the displacement. Now we've plotted our points and the measurements we've taken, and we put a best fit line, and we get an equation that says y equals 6x with an r squared of 1, which means all the points are actually on the line. So if we examine the equation, which is of a line, y equals mx plus b, we put in our constant, which is the slope, 6x. The y-intercept is 0. We see there's no 0 value given here. There's no value given here for y-intercept. So the y-intercept is 0. So we have an equation of y equals 6x is the line, and that's why we have this here. Well, the y-axis, the vertical axis, is the force applied. So y becomes the force applied. We have our 6. And the x-axis is the displacement, the elongation compression, delta x. Now we said Hooke's law is force applied equals k delta x. So what should be a big takeaway here then is that the slope of the graph is the spring constant. The slope is constant because it's a straight line. And this is how we interpret a Hooke's law graph. If we're graphing force and elongation, the slope of the line will give the spring constant.